Okay, so the video was cut for some reason at that point, and I was explaining the how we carry out this integration. Okay, so let's continue from there. So to find the CDF, we integrate as always from 0 to x our PDF. Okay, and it turns out that this integral is equal to sinus square x. Then we take the inverse of this. Okay, we take the inverse of this. And the inverse of the CDF becomes equal to this. Okay, so this is the inverse CDF, which means that we are going to find our sample value. Okay, we are going to find our theta here. Theta I is going to be the inverse CDF psi, let's call it this time 2i, okay, which is equal to sinus minus 1 square root psi 2i. Okay, so with this we can now, if we generate samples with respect to these random variables theta and phi computed from chi 1 and chi 2, we give more probability to vertical to directions that are closer to the zenith of the sphere. Okay, now again let's simplify these things a little bit here. So if you remember, let's draw what are we going to do is we are going to compute again connecting this to the previous video. So we are going to have LU is equal to sin theta cos phi, right? That's what we call LU. I think we call it LU prime. LV is equal to LV prime is equal to cos theta, and LW prime is equal to sin theta sin phi. Okay. So what were these angles? These were what were these components? These were when you create a orthonormal basis, okay, around the direction that you are sampling. Okay, so let's say this is N and V, this is U, and this is W. Okay, so we generate a vector here, L. Okay, and we call this theta, and we call this phi. Okay, so from this geometric configuration, so assume that there's an orthonormal basis U, V, and W, and the U component. So if you have a vector L which makes an angle of theta with the V and phi with the U axis, then LU prime is going to be sin theta cos phi, LV prime is going to be cos theta, and LW prime is going to be sin theta sin phi. Okay? Now, okay, so here we have these things. So if you plug this in, LU prime, your LU prime is going to be LU prime sin theta. Okay, so sinus, and this is theta, right? So sinus minus 1 square root of psi 2i. Okay, and then cosinus phi. What is phi? Phi is 2 pi chi 1i. Okay, so as you can see, these two functions cancel out each other. So here you end up with simply square root chi 2i. Okay, now LV prime is equal to cos theta. So it is cosinus of sinus minus 1 and square root chi 2i. Okay, so it is cosinus of sinus. So to make this more efficient, we can actually simplify this. Okay, so this is an angle, right? This is an angle. Let's call this angle alpha. Now, if you draw a configuration here, let's say we have alpha, and we have 1, okay? And we have, let's say this is chi 2i, okay? and this is what is it going to be? It's going to be square root 1 minus chi 2I. Okay, so the square, this is a perpendicular triangle, so the square of this plus the square of this is going to give us 1. Okay, so here we can see that sinus alpha is equal to square root of chi 2I. Okay, now the inverse of this, then if you put here, let me show it with a different color. If you put sinus inverse, okay, of this, you put sinus inverse here, you are going to get, this is going to cancel out, so you are going to get alpha here. Okay, so alpha is then this one. Okay, so we are finding cosinus alpha. Then what is cosinus alpha from this geometry? Cosinus alpha is equal to, then from here, cosinus alpha is equal to 1 minus chi 2I. Okay, so for simplification, so here we can clean all of this and we can write 1 minus chi 2I. Okay, and then this is what it is, and then for LW we can write again square root chi 2I sinus 2 pi chi 1I. Okay, so with this we find the components UV and W components, and obviously we can find our global light vector as follows. L is equal to U times LU prime plus V times LV prime plus W times LW prime. Okay, so UVW vectors. And how do we create UVW vectors? Is we create an orthonormal basis from a single vector from the N vector. So the L vector that is created like that, the light vector, with this formulation is going to be, the probability of that is going to be higher, closer to the directions that are closer to N. So it will give more probabilities here and less probabilities here. Okay? So this concludes our lecture on sampling, the theory of sampling that we need for Monte Carlo ray tracing.